Thank you, Wolfram, for this extremely important announcement. So welcome back to the afternoon session. I'm David Su from the National University of Singapore, and I'm going to chair this session. Right. The first paper of our session is Leveraging Experience in Lazy Search by Mohak Boawaji, Sanjaban Chaudhry, Byron Boots, and Sid Srivastava. And Mohak is going to give the talk.
Hi, everyone. I'm going to talk about motion planning. So robot motion planning is often formalized in the terms of piano movers problem, where the task is to move a piano from one room to another and find a collision-free path for it. And one way to formalize this problem is to find the shortest path on a roadmap, where the nodes are the robot configurations and the edges are motions between the robots. And we use some sort of graph search to find the shortest feasible path on this graph. So one popular method to solve this is using A-star search. But as you can see above, A-star search actually checks all these edges in blue, which are actually feasible. And this is not what we really want in motion planning, because edge evaluation is the computational bottleneck in motion planning, as it requires a lot of collision checks between the robot model and the environment model. And it has been shown that it can actually take almost 100% of your planning time. So in order to address this, Delin and Srinivasa actually present the lazy SP class of algorithms, which try to explicitly minimize the number of edge checks by taking the concept of lazy search to its limit. And it works as follows. So you start off by doing a lazy search for the shortest path without evaluating any edges at all. Then you start evaluating it using some heuristic, say the first edge on the path, till you find something that's in collision. And then you update your graph with this new information, and then you do another lazy search with this updated graph, and you use your heuristic again, start like selecting edges on the path till you find something else that is in collision, and you continue this process till you finally end up with a collision-free path from the start to goal that you've evaluated. So using the first edge on the path is good, and there are many heuristics that exist, but the question is, what is a good efficient selector? And the answer for that is an efficient selector eliminates a lot of paths quickly. And to think of this, think of moving a piano in a new house, right? So which edges would you want to evaluate here? Well, you probably want to check the doors first, because a lot of paths pass through the doors. And you might want to prioritize narrow doors, because then you probably don't have to check inside the rooms, because these are likely in collision. And you would want to prioritize narrow corridors, because edges here are correlated, and they will better inform your posterior over the other edges. So our key idea is that we want to leverage such intuition to get by imitating a clairvoyant oracle. And what is a clairvoyant oracle? Well, imagine I told you all the statuses of all the edges on this graph. What would be the optimal set of edges to evaluate to eliminate all shortest paths? And the answer is set cover. So using set cover, you can see that all you need to do is evaluate those three shortest paths, three edges, and you'll end up with the shortest path. And what we want to do is we want to imitate this oracle to learn an efficient selector from data, because executing this oracle online can be computationally very inefficient. So we want to utilize imitation learning to learn a selector from data. And this is an example of this running in practice. So here, the learner actually trained on a data set of bug traps learns to actually detect the bug trap and get out of it, whereas a heuristic selector, which is uninformed, does not know what to do. Similarly, this is called a baffle. In this case, the learner focuses the search only along the walls and is able to eliminate many paths quickly and outperforms like uninformed heuristic selector. And we ran our approach on a lot of benchmark data sets, and we found that the important features were the posterior and centrality of an edge. So centrality here tells us how many paths actually pass through this edge. And our key takeaway is that experience is essential for making motion planners faster. And for more information, please meet me at the poster session. Thank you.
Our next paper, Learning to Plan with a Logical Automaton. The paper is by Brendan Araki, Kieran Bodrali, Thomas Leach, Christian Vassal, Mark Donahue, and Daniel Rus. And Brendan is going to give a talk.
Hello, so my name is Brandon Araki, and I'll be talking about learning to plan with logical automata. So many environments have simple rules. For example, cooking from a recipe, playing games, driving, and assembly. So people can learn to perform these tasks by watching an expert. But notably, people don't learn to just mimic the expert. They learn the rules that the expert is following. Therefore, a person who has learned to cook a dish can easily modify the recipe and make a new dish. So our goal is to replicate this ability algorithmically using model-based imitation learning. So this consists of two sub-goals. One is to learn the rules in a way that they can be easily interpreted by humans. And two is to incorporate the rules into planning so that modifying the rules results in predictable changes in behavior. So I'll be referring to this environment for the rest of the talk. The robot has to pack a lunchbox, and the rules are that it has to first pack a burger or a sandwich, and then pack a banana. So we can make rules useful while maintaining interpretability by representing them as a finite state automaton. So in this case, the rules are pack a burger or a sandwich and pack a banana. And we could represent that as an FSA, where we have an initial state, and then picking up the burger or sandwich leads to the next state. Putting that into the lunchbox leads to the next state. Picking up the banana leads to the next. And finally, putting the banana in the lunchbox leads to the final goal state. So we assume that the Markov decision process of the environment can be factored into a high-level MDP equivalent to this automaton and a normal low-level MDP. So you can imagine that we have a reinforcement learning robot arm simulator with state x, y, theta, et cetera, and actions such as torques or commanded positions. So we assume that there's also a high-level MDP that is equivalent to the FSA and which embodies the rules that the robot must follow. So to reiterate, we represent the high level as a finite state automaton and the low level as a discrete 2D grid world. So we want to be able to modify the behavior of the agent in order to make it perform similar but new tasks to the one it has learned. We achieve this by incorporating the FSA into a recursive planning step. Since FSAs are graphs, they can be converted into a transition matrix. So before illustrating this, I'll label each FSA state with a name. So we start with S0, S1, S2, et cetera. And here's the transition matrix of the first FSA state. So the columns are associated with features of the environment, and the rows correspond to FSA states. You can see by looking at the graph that, that the sandwich and burger cause a transition to state S1, whereas the other items do not cause a transition to a new state. So we use differentiable recursive planning to approximate value iteration and calculate a policy for the agent. The matrix form of the FSA allows us to embed the FSA as a convolution in the planning step. And if you'd like more details, please come to our poster. So this is the learned transition matrix of the first state of the FSA. So columns correspond to propositions or important features of the environment, and rows correspond to the other FSA states. So we can see by inspecting the learned model that picking up the sandwich or the burger causes a transition to the next state. Since we have learned an interpretable model of the rules, we can easily modify the rules to change the behavior of the agent. So let's say that we want to modify the FSA so that it will only pick up the burger and not the sandwich. We can do this by just deleting this edge between the initial and next state. So this change is also easy to express using the transition matrix of the FSA. So we can change the values in the matrix to change the form of the FSA. So in this case, if we delete the transition associated with the sandwich and replace it with a new transition that just leads to the current state, that affects the same change that we made to the FSA earlier. Yeah, so thanks for your time, and if you have any questions, please visit me at the poster session.
Our next paper, BayesSim, Adaptive Domain Randomization via Probabilistic Inference for Robot Simulators. Paper is by Fabio Ramos, Rafael Pozas, and Dieter Fox. And Fabio is going to give a talk.
Hi, my name is Fabio Ramos, and this is a joint work with Rafael Pozas and Dieter Fox at NVIDIA. We are producing very powerful simulators. These simulators have beautiful equations inside connected with solvers. And in this work, we want to treat simulators as black box generative models where we can forward simulate them to generate a prediction of what reality should be. Well, the problem is, once we observe reality, we'd like to infer what's the parameters of the simulator that best describe this reality. This process is known as inverse modeling, and unfortunately is multimodal in many cases. So there are different configurations of values and parameters that give you the same prediction for the reality. So what we are interested in this paper is to study how do we capture the uncertainty of these simulators. Well, we propose BayesSim, which is known in statistics as a likelihood-free inference engine. It works in the following way. So first, someone proposes a prior distribution over simulation parameters, which is then used to sample several simulators. Each one will generate a prediction of reality, which are then passed to BayesSim as features in time. We can then observe one or more real observations of the trajectory, and BayesSim will combine all of this and give you a posterior, a joint posterior over the simulator parameters. What you see in this plot is the joint posterior for mass, pole, and length for a problem known as the pendulum. And you see the bimodality that you generally observe in problems like this. Now, the question is, giving access to a joint distribution or the posterior for a simulator, how can you use that? One application is in domain randomization, either for control or reinforcement learning. If you have a closed-loop problem, as you see in there, randomizing over prior is generally sufficient. As you see, the robot here can control the block quite well. But in other problems, such as sliding, just randomizing over a prior distribution might not be sufficient. We need to have a much more precise idea of the uncertainty over, let's say, friction. BayesSim provides that posterior. As you see here in the blue line, BayesSim compared to other likelihood-free inference engines in statistics, we generally provide a posterior that is more peaked around the true value represented by this vertical red line. Okay, now that we have a posterior, we can then randomize and learn a new policy over the posterior rather than on the prior. This is seen in this graph, where we achieve a much better rewards with converging much faster than if you were just randomizing over the prior. More interestingly, we can plot the performance of the policy strain against the parameter values, the true parameter values, and we see here that for push and slide, the performance of BayesSim or policy strain on the posterior against the policy strain on the prior, and generally BayesSim provides a more solid and more robust answer. Now, here's the final message, and I hope you can see me at the poster. All simulators are wrong. Some simulators are useful, but with BayesSim, many together can be much more useful. Thank you.
Very nice. The next paper, Online Incremental Learning over the Terrain Traversal Cost in Autonomous Exploration by Miloš Prager, Peter Chizek, Jan Behr, and Jan Feigl. And Miloš is going to give a talk.
Hello, everyone. My name is Miloš, and in this spotlight, I would like to draw attention to our paper, where we present a robotic system for simultaneous exploration of spatial environment model and its underlying traversal costs. Well, what are the main components of our system? First of all, our system must localize itself in an unknown environment and build a representation of its surroundings. This representation is used to reason about the traversability of individual terrains. First, unpassable areas are filtered out, and then the robot learns and uses a traversal cost model for the passable areas. So the traversal cost model is learned by the robot incrementally while traversing the different terrains in the environment. And the model is then instantly used in navigation. Finally, the robot fully autonomously explores both the spatial model and the traversal cost model. To explore the traversal cost model, we reason about the uncertainty of the costs of the cost model. To do that, we deploy the Gaussian process regression. Basically, we use the Gaussian process regression variance to represent the uncertainty. However, Gaussian process regression suffers from relatively high computational complexity, especially in learning, while in exploration, we need fast or even instant model updates. Therefore, we used a robust BayesSim committee machine to combine a set of smaller Gaussian process regressors into the full traversal cost model. So now, back to the maps and the components of the system. The robot basically tracks several maps. First of all, we have the environment map, which contains elevation, color, and terrain feature descriptors that describe the environment and the terrains. The elevation information is used to filter out the unpassable areas. And we basically compare the elevation of neighboring cells to filter out obstacles such as walls or ravines. Then the terrain feature descriptors are used to learn and to predict the traversal costs. We have two types of traversal cost maps: the traversal cost predictions, which basically are the Gaussian process, basically the Gaussian process prediction mean, and the the uncertainty map, which is basically the Gaussian process predictive variance, or rather the square root of the Gaussian process predictive variance in our case. Finally, we use the spatial map and the uncertainty map to compute the exploration goals for the spatial model and traversal cost model exploration, respectively. So the traversal cost model is learned incrementally by the robot while walking through the environment. The robot basically pairs up the experienced traversal cost and the terrain description and its respective areas to learn the model. Now, about the exploration. The spatial exploration is basically a traditional frontier-based exploration, while the traversal cost model exploration navigates the robots towards the areas of the greatest traversal cost model uncertainty. We combine the two exploration types based on the uncertainty, or on the highest uncertainty on the map. The robot basically explores the traversal cost model if the uncertainty is over a given threshold. Therefore, the robot greedily explores unknown terrains if such unknown terrains are available. If you are interested, we are happy to answer your questions during the following Q&A session or in the poster session in the afternoon. Thank you for your time.
Our last paper of the session, Robot Adaptation to Unstructured Terrains by Joint Representation and Apprenticeship Learning, by Sriyan Siva, Maggie Wignis, John Rogers III, and Hao Zhang. Neil Denton will speak on behalf of the authors.
Thank you. So this is collaborative work between the Colorado School of Mines and the U.S. Army Research Lab. And apologies from my colleagues who couldn't be here due to visa issues. So this paper addresses the problem of adapting robot navigational behaviors to familiar and unfamiliar unstructured terrains in complex field environments. Autonomous mobile robots have increasingly been used in field environments to address real-world applications. When deployed in an outdoor field environment, mobile robots need the essential capability of efficiently navigating through different types of terrains with a wide variety of characteristics. Thus, the capability of generating desired navigational behaviors that adapt to unstructured terrains is essential for an autonomous mobile robot to operate in these complex field environments. To solve the problem of robot adaptation to unstructured terrains, we introduced the principled approach called Terrain Representation and Apprenticeship Learning, abbreviated TRAL. The contributions of this paper are integrating representation learning and apprenticeship learning under a unified, regularized optimization framework, identifying and fusing important heterogeneous terrain features that are discriminative for both terrain classification and robot adaptation, and developing an optimization solver that solves the formulated joint representation and apprenticeship learning problem. So the first loss function in TRL is defined as the error in predicting terrain types to ground truth for terrain classification. The second loss function is designed to transfer human expertise to the robot through direct expert demonstration. So you can view this as a projection from feature space to behavior space. So the regularized terms have been introduced to model the underlying importance of feature modalities in terrain classification and behavior generation. So as different terrain features capture different characteristics of the unstructured terrain and contribute differently towards terrain classification, we introduce the C norm that enforces sparsity and feature modalities to identify the most discriminative feature. And then the A norm is introduced to enforce sparsity among feature modalities with respect to all robot behaviors, which helps identify discriminative features for behavior generation. We also introduce a principled integration of representation and apprenticeship learning in this unified framework. So to evaluate the performance of TRAL, we collected diverse proprioceptive and exterioceptive sensory data from the sensors mounted on the mobile robot. So in addition, we have expert controls of the mobile robot recorded during navigation. So we first test on familiar terrains. In this experiment, we test for 5 types of terrains and then train for 5 types of terrains and then test on only those 5. So we use root mean squared error and error rate as metrics. The overall performance compared to previous apprenticeship learning methods is here. So TRAL offers superior performance for both root mean squared error and error rate. So we next test over unfamiliar terrains. So we train here on 4 terrains and then test covering 5 different terrains. So including one not seen during the training phase. And then again, TRAL is giving better performance compared to these previous methods. So results on learning importance of feature modalities towards terrain classification and robot adaptation is shown here. So we observe that features from the inertial measurement unit are relatively important towards both terrain classification and behavior generation. We also note that TRAL is fast, so we can perform at 20 hertz with feature extraction, and without feature extraction, we can perform at 80 hertz. So thank you very much, and please come to the poster if you have more questions. Thanks.
Can I have all the speakers lined up for the Q&A session? Yeah, questions?
Oh, hello.
Yeah.
Hey, I would like to ask you ask a question about the BayesSim. So, how do you? It's really a great and impressive paper, but I wonder that how do you select the real-world policy to be executed on the real world? I guess it has a huge impact on the real-world data collection. And if we have more and more data from the real world, then would the performance be increased?
Great question. So for some experiments, even random policies will be okay. For example, for pendulum, it's easy, even if you start with a random policy. For fetch and experiments that actually involve a robot, you need to excite the parts of the state space that really requires more data. So if you just do a random policy, it's not going to happen. What we did to collect our experiments was we picked some policies available. They were pre-trained on a specific set of parameters and used those to collect the data. But yes, the more data we have, the better, up to a certain threshold, where beyond that, the uncertainty cannot be reduced, and the only way you can reduce that further is if you have more real observations. So we keep on building a posterior over another posterior and so on. And then the posterior would shrink and be of higher quality. Thank you for a question.
Over there. Mike.
Thank you. Question about the first talk. So you learn from an oracle from previous planning problems where to cut edges. And now my question is, you can learn other things, right? You can also learn how to predict the motion plan, and you can learn where to sample, and there's been works that try to do that. And I'm wondering if you have, if you've compared to these methods, or do you know why learning where to cut edges is preferred in some sense?
Thank you for the question. So the main motivation here is from where the actual computational bottlenecks occur in motion planning, which is actually edge evaluation. So it makes sense to actually try to address that problem. And another way to look at this is as you're actually trying to reject a lot of hypotheses really fast. because doing every individual test is very computationally expensive. So you want to minimize the number of tests you do. So that's why we focused on the edge evaluation problem. Thank you.
Question for Fabio. Oh, sorry. Thank you. Question for Fabio. Because of the comparison with domain randomization in a simulator, there are many bulbs where you can introduce noise. So the question is sort of about the scalability of the approach in a situation where there could be 100 parameters where there could be distributions for noise.
Yeah, so the scalability in terms of the number of parameters, you can effectively produce decent posteriors, right? It's difficult to give you, a number of that. I would say that up to 10, 20 parameters, we can recover posteriors relatively well, even if they are highly coupled. If posteriors are, if the variables, the parameters are entirely uncoupled, then you can produce posteriors for a much larger dimensionality, right? But I would say we cannot, at this stage, do joint inversions for more than, let's say, 20, 30 parameters, and we're still experimenting with physical problems, right? The impact of the noise, the acquisition of the real data and the noise, and how these posteriors are affected. But we can talk more in the poster.
Another question? Okay, so I have one question for Miloš. So I wonder whether you can comment on computational efficiency, how big of a scalability, how big of environments you can handle, and whether you can do that online or offline. And
we basically tested our approach in a laboratory environment. Generally speaking, few meters by few meters. And at the most, the learning is more or less fully online. The prediction may take some time because we evaluate the full grid for the prediction mean and variance. So that may take some time, in matter of seconds at most.
Okay.
Yes.
Yeah. So, more questions? No? Okay, I'll ask one last question. Brandon. So I think I may have missed something about what you said about learning to plan. So the planning part, is that you actually manually embed it in there, or you actually try to learn?
Yeah, the planning part is like part of the network. So we have a recursion in the network.
So you manually code it into the network?
Yeah.
All right. If no more questions, we end this session. Thank you. Let's thank all the speakers again.